Hi folks, welcome back to Physics with Captain Rod. We're going to talk about 21 here for a little bit. All right, so it's this spaceship again, and this time it's asking for how many radians of rotation will it take the thrusters shown to get that spacecraft at the correct rotation rate. So remember, right, we have these 2,000 Newton force vectors. Right, that are acting like this, and they are giving us an angular acceleration in that direction. And in your previous problems, you should have a number for that in units of rad per second squared. Now, there's a couple different ways we can attack this, and let me talk about both of them. We can attack this from just, I think, a pure motion standpoint or an energy standpoint. And let me talk about both. All right, so motion-wise, if you have the angular acceleration and you have the final angular velocity, which you do, if you plotted now a graph of angular velocity against time, right, it starts from 0. And then, a little time later, it has a new angular velocity, and a little time later, a new angular velocity, and a little time later, a new angular velocity. Now, eventually here, right, this is going to end at some time t and some angular velocity that we know. And I think you know both of these values, because I think you calculated this in the last problem and this in the last problem as well. Now, look at the units. The angular velocity is in radians per second, and the time is in seconds. So if you think about the product of those two, that comes out in radians. So just think about, how the product of the two relates to that graph. And that will tell you the change in theta. Alternatively, we can also attack this by principles of work and energy. So if we call position 1 at rest and position 2 when it's rotating, and we write out the work energy theorem, and we start thinking about this term by term, okay, there are no potential energies to worry about in this problem of any kind. The kinetic energy is, the KE1 term is 0 if it starts from rest. Okay, now the work term. The work term can be expressed as torque times change in theta. And the KE2 term can be expressed 1/2 I times the angular speed squared. And this you can look up and calculate. This you have from previous problems. This, the torque. All right, now let's look at our picture, our free body. You've got 2,000 newtons times this distance clockwise. And you also, on the left, have 2,000 newtons times this distance. And again, they're both clockwise. So that should allow you to calculate the net torque. And you can get the change in theta out of that. So I think in my future versions of this problem, I'll probably have a part A do it this way and part B do it this way. But anyway, I hope that this helps. Have a great day.